All right, let's get started. So today we're going to start a unit on what's called simple linear regression. And we'll see what that means in just a moment. All of our lectures will involve some sort of data set to illustrate the concepts on. And in this lecture, we're going to use a data set where you have a bunch of data on different aspects of vehicles like miles per gallon, number of cylinders, horsepower, weight, etc. And with that data set, you could construct various prediction problems. And so the problem we're going to construct for ourselves, just for illustration, is we're going to try to predict the fuel economy in miles per gallon of a vehicle from things like number of cylinders, horsepower, weight, etc. So as we go through these lecture slides, there's going to be screenshots of code, Python code that is from a Jupyter notebook, which is in the GitHub repository. If you have access to the repository, you can just click on this green link and it will take you there. The data is coming from the University of California at Irvine library. They have tons and tons of data sets for machine learning, so it's just one of the thousands that they have there. And so what I'm also teaching you in these lectures is a little bit about how you do the coding for these sorts of problems. And so we're going to talk just a little bit about how you load in the data now, because that's something you always have to do as the first step when you work on a machine learning problem. So the ideas in this lecture, in this unit, are super simple. So I apologize if they seem overly simple, but don't worry, the course will definitely get more complicated as we go on to future units. Okay, so starting with how you load the data. In Python, the Pandas library is the main way that people load data. It has tons of useful features to do this. But there's also lots and lots of settings and lots of complexity with how different data sets can look out there in the world and what you have to do to load them. So I would say, especially with regard to Pandas, Google is your friend. If you have questions or if you're seeing strange errors, just Google them, and that's the best way to figure out what's going on. So the main command to read in data in Pandas is this read CSV command. And what it will do is it will create a data frame, which is an object that has a bunch of data and a bunch of functions and stuff in it. And there's three main components to this data frame. There's the values, which are going to be the actual numbers from the data. And they're going to be in NumPy format. NumPy is the kind of main numerical library that people use with Python. And it's going to have columns, which are the labels of the columns, and an index variable, which are the labels of the rows. So to see what I mean, here is sort of a visualization of what we get when we load in the data from this automobile. What's it called? Auto MPG. That's the name of the data set. So here you can see all these numbers. Those are the values. You can see these numbers here. This is the row index. Each one of these rows is what you would call a sample in the data set. And each of those samples has a bunch of different values, and those are what we call the features, or there's other names. We'll get into that later too, but you can see that the first one represents miles per gallon, the second one represents number of cylinders, and so on and so on. And the last one is the name of the car. So, okay, how did we get this? Well, the very first step, many of you who have used Python, you already know this, but in case you haven't, basically what you have to do is you have to load in the different sub-packages or libraries you want to use. So we're going to import Pandas here. And the other thing we do is we typically abbreviate them so that when we code, we don't have to type in Pandas over and over again. We're going to abbreviate this as PD. So that when we use this read CSV command, we have to tell Python that this is a command within the Pandas library. And so we're going to do pd.readCSV. So now our Python interpreter knows where to find that command. And you can see that when we ran this, we had to give it a bunch of inputs. So we had to tell it, first of all, where to find the library. And so here you can see we're giving it this internet address. It goes to the UCI repository, downloads that particular data set. But we also have to tell it many other things about how that data is formatted. And often you have to just do this by trial and error, because you don't necessarily know how the data is formatted before you download it. And so maybe you just have to try some things to get it right. So for example, the data set may or may not have a header, which is a bunch of lines that's not the data, but kind of stuff about the data. This particular one doesn't have a header, so it works to write header equals none. Another thing is, how are the numerical values separated? Are they separated by commas or spaces or different lines? You know, and so here, that's this delim white space. By setting that equal to true, that works well with this data set. Now we also have to tell it what are the names of these columns. So it turns out that those are not actually in the data set. Those are in some description of the data set that you have to read about and know about. And so we are supplying them manually by making this list of strings here called names. And so we're going to give that list of strings to our read CSV command. And the last thing we're going to tell it is how to deal with missing values. So in this data set, if there's a numerical value that's just missing, it's going to be represented with a question mark. So we're going to tell read CSV, that's what the question mark means. And then finally, this creates this data frame object for us, which we said over here has these three main components, but it actually has a lot of other stuff. Like it has functions inside it. So if you want to print out this stuff, you use this head function. And the head function takes an argument, which is how many rows do you want to print out? So here we're telling it to print out the first 6 rows, and it prints them out in a nicely formatted way so you can look at the data set, understand what's going on. Okay. All right, so moving on. Once you have that data loaded, we really want to try to visualize it, because visualizing it, you can learn a lot about it. You can notice if something is really wrong, or you can just, as a human, we're pretty smart, and we're noticing trends and stuff. You can see maybe there are certain trends in the data that can be exploited. So in order to visualize things in Python, the main library people use for this is matplotlib. And what it provides for you is a bunch of very MATLAB-like functions for plotting. So here we're going to import the matplotlib package, but we're also going to import a sub-package called pyplot, and we're going to abbreviate that as PLT. And then there's one more line that we use within a Jupyter notebook that tells this particular package to print, to put the figures within the Jupyter notebook rather than like opening another window or something. So this is how we set up our plotting environment. And now, in order to do the plot, first we have to extract the data, the numerical values from that data frame. So in particular, what we're trying to do right now is we're trying to plot displacement versus, or miles per gallon versus displacement. So in other words, we're trying to plot this column versus this column, just to see how those two quantities relate to each other in our data set. Okay, so what we have to do is we have to get these values into a vector, and we have to get these values into another vector, and then we can plot the first vector against the second. So when we're working with this data frame, we can actually refer to these things by their column name. So rather than saying like, I want to load in the first column, you can say, I want to load in the mile per gallon column. So here we're going to make, miles per gallon as a string. We give that to the data frame object. It knows to pull out those values. And then we're going to format them as a NumPy array. So here, NP is this NumPy package, and this is a command that formats that as a NumPy array. And then that's just, it's convenient because a lot of the numerics we do will involve NumPy, and they have to be formatted in a way that NumPy understands. So And then that's to get y. To get x, it's very similar, but we did it in just a slightly different way. So you could see at first we put displacement, that string, into a variable, and then we fed that variable into the data frame, and that was able to extract that displacement column, put it in x, and now we can finally plot things. And if you look at these, if you're familiar with MATLAB, how many of you guys are familiar with MATLAB? Right. So, and another question, how many of you feel more comfortable in MATLAB than Python? How many feel more comfortable in Python than MATLAB? Okay, that's great to know. So anyway, if you're already familiar with MATLAB, then these commands won't look too strange, and if you're already familiar with Python, you probably know all this stuff already. So anyway, if we want to make this plot, we can just use the plot command. You give it the first column, the second column, and then rather than plotting lines between points, we're actually just going to plot dots. And so we can do this with by telling it to plot one of these little markers at every location. There's also another command, the scatter command. We could have used that too. We'll see an example of that in later slides, but here we're using the plot command. And then we can decorate the axes with these labels here. We can do that with X label, with Y label, and we can add these grid lines and so on. And that just makes everything a lot more interpretable so we can see exactly what's going on. Okay, so this is what the data looks like. Displacement of the engine, this is in cubic inches on the horizontal, and then vertical we have the miles per gallon. So the question now is, what relationships do we see? So here's a couple other things we could have also done. We could plot miles per gallon versus horsepower, miles per gallon versus acceleration. And now let's just step back and think for a moment. When you look at these plots, do you see a predictable relationship? Do you see a mathematical model relating one variable to another? What do you think? Let's look at the first one. If I told you the displacement, do you think it's possible to predict the miles per gallon? Kind of, right? What about horsepower?
Yeah.
Kind of. What about acceleration?
Less so.
Less so, right? Exactly. So in your mind, I think what you're all probably doing is you're sort of imagining like that there's some sort of curve that the data is more or less lying along, right? And that is exactly what we're doing in these first few units of the course. We're thinking of ways to make sort of like a prediction function. Like if this is my prediction function, then it says, well, if you give me a new horsepower of a car where I've never seen it, then I should be able to predict more or less what the miles per gallon of that car would be. Okay, that's the essence of it. We're just going to get into all the, formalism of all this, how you do it properly, what kind of errors you expect, putting theory behind this, learning how to do all the coding for this. But that's exactly the idea. So in this unit, though, when we talk about linear regression, what we're actually doing in most cases is we're fitting this with a line rather than a curve. Although, as we'll see towards the end of this unit, it is possible to non-linearly warp our data beforehand. Maybe we warp one of these axes, and after we warp it, then the data can fit on a line, and then we can apply a line, and it works really well. Okay. So just stuff to think about looking forward, but that's kind of the gist about what we're doing right now, is we're looking at the data, we're trying to see, is there a model there that can be exploited for prediction? All right. Any questions so far? Okay, great. So again, we're going to focus on linear models. So first, we have to get a bit of terminology down because terminology is important. We need to be able to speak the same language as other people doing this stuff. So here in this unit, we're making the problem really easy in that we're only going to predict one scalar quantity from one other scalar quantity. So there's just two numbers. It's not like in reality you might say, well, miles per gallon is really a function of all these different things, horsepower, displacement, blah, blah, blah. And so yes, it would be better if we could use all that stuff. And that's what we're going to do in Unit 2. But in Unit 1, we're going to be super simple. We're just going to predict with one single thing. So the variable that we're trying to predict, we're always going to call that y in this course. And we're almost always going to refer to it as either the target or the label. Though it is good to know that in other books and other fields, they refer to it by various other things, such as the regressand, the response variable, the dependent variable. Especially in statistics, they use these terms. And it's good to know about them because maybe you're reading something else, and if you don't know what they mean, you just have no idea what's going on. Okay, so that's what we're trying to predict, y. So in this case, miles per gallon would be the y. And the variable that we're using for the prediction, we're going to call that x all throughout this class. And we're usually going to refer to it as the feature, or maybe multiple features. So that's going to be our main name, but people also refer to them as predictors, regressors, attributes, independent variables, and so on. And again, focusing on single variable in this unit, next unit, multiple variables. So that's what we're doing. We're basically trying to predict something like y miles per gallon from x horsepower. But in order to do this, we have seen many, many examples. Those are all those blue dots. And that is our data. So mathematically, we would say that the data is a set of pairs xi, yi, where I is used to index across those pairs. So each one of those blue dots has a different I. And we're going to have a total of n pairs, or n samples in our data. So each one of these pairs is called a sample. Oops. And we have n samples total. And we're going to use that throughout the whole semester. N is always going to be the size of our data set. And then this plot on the right is called a scatter plot. And so we'll see a lot of those throughout the term. All right. So that's just kind of setting up the terminology. And so here, if you remember, I mentioned that I'm going to have some blank stuff in the notes just to try to keep you guys a little bit interactive. So here's a couple equations that I left blank, but I'm going to fill them in now. Okay, so for this linear regression problem, we said we're going to assume a linear model. So mathematically, what does that mean? It means we're going to assume a particular relationship between x and y. And the way we're going to write it is we're going to write it as beta 0 plus beta 1x. So we're going to say y is approximately equal to beta 0 plus beta 1x. And if you look at this red line here, this red line is showing this equation beta 0 plus beta 1x, right? So beta 1 is going to be the slope of that line. So beta 1 is the slope. Beta 0, where's beta 0 on this plot? It's the intercept. It's the place where this line crosses the y-axis, beta 0. So sorry if this is a little hard to read. Beta 1, beta 0. But notice that there's an approximate sign here. We're not saying that the data is exactly on the line. We're saying that it's approximately on that line. And you can see that all the blue points are actually off the line, right? That's the reality with data, is it never fits your model perfectly. You don't expect it to. The model is just a rough approximation. Okay. But we do have to make a prediction at the end of the day. So someone, sometime later after we have decided on our model, is going to give us a new vehicle, and maybe that new vehicle has a feature value that's like 37, whatever this is, and then we want to make a single prediction. So what we do is we plug in that value into our model, and that gives us this prediction y hat. So the hat is indicating that this is like our guess, our prediction of the true y. So that y hat would be this value. So if this is x down there, then y hat we get according to that red line. Is everybody with me so far? Okay, so that's really the essence of what we call simple linear regression. The word simple means we're only using one variable. Multiple linear regression we'll do in the next unit when we use more than one. This line, this red line, is called the regression line. Slope of beta 1, intercept of beta 0. Those coefficients, beta 1 and beta 0, those are the parameters of our model. Those are the things that we don't know what they should be. Someone gives us a bunch of data, and we fit the parameters to our data. That's the learning. That's the machine learning. Once we have our model, once we know those betas, we can just apply it. Yeah.
Is the triangle on top of the equals just like predicted equals?
Oh, yeah, great question. So this notation here, this means definition. So whenever you see an equals of the triangle, that means I'm defining a quantity. So I'm just making up a new relationship. That's what a definition is, right? So I'm just making up this new term, y hat, and I'm saying that by definition is just equal to that. So, okay. So you might ask, well, why are we using this linear model? It's so simple. Maybe it's too simple. You're right, it is extremely simple. But it's a good place to start. It's very easy to interpret. It's very easy to analyze, we'll see. It's also very easy to optimize the parameters, to find the beta values that are optimal. We can do this with a little derivation. We can find the numbers with an equation in closed form. As we'll see, it's going to depend on how we set our loss and so on, but we're doing this out of simplicity, not because this is necessarily the best model out there. All right. So we kind of set up the model. So now the question is, how are we going to figure out those parameters? So the first thing we have to do is we have to be a little bit more concrete about the error in the model. So for this, again, we're going to notice that we don't have an equality in our model. We have this approximate equality. And so we're saying that y is approximately equal to beta 0 plus beta 1x. But let's be a little bit more concrete now. Let's rewrite this as an equality, but with one other variable that tells us what the error is, the difference between the model and the actual data, or the truth in this case. So we're going to write this as beta 0 plus beta 1x plus epsilon. So epsilon we're going to call the residual, and when we have this residual, now we have an equality down here. So, okay. So, so there's sort of two ways to look at this. One way to look at this is in terms of generic quantities x and y. So when we talk about generic quantity x and y, we're talking about like, where you are on this axis, where you are on this axis, just generically. But if you want to talk about the data specifically, which is what's happening at this point or what's happening at that point, we have the same equation, but we just have little subscript i's. So like if I want to talk about what's happening in the ith data point, well, one thing we saw earlier is that our prediction of what the ith y is going to be from this linear model. But we can also write, for example, yi equals beta 0 plus beta 1 xi plus epsilon I. And now we're talking about epsilon I would be the actual difference between the true data yi and our prediction yi hat. So let me give you an example. Maybe we're talking about this value here. So let's see. So maybe this is xi, and so yi would be here. I'm looking at this particular value. And so what would the y hat I be in this case? Where would I find that?
Correctly on
It would be exactly on that red line, right? So this is my y hat I. And now do you also see where the epsilon I would be? Epsilon I is the difference between the truth and our prediction, right? You can get that from those last two equations. So what is epsilon I in the graph? Yeah, it's just the difference from the dot to the line. So it's, I'll do this in green. So this is epsilon I is this. So if you want to think about like all the different epsilon i's, you can think about all the different lines that are, these are all the different errors in the model for all the samples. So essentially what we want to do eventually is we want to adjust that line, choose the parameters beta 0, beta 1, to somehow make those errors small, right? Because the smaller we make those errors, the better the fit between our model and the data. But in order to do that, we have to be concrete about, well, we have like a way of measuring the error, but we need to say like, what matters about the error? Is it we want to look at the absolute value of those errors or the squared value or something else? So that's where we have to be a little bit more explicit about a loss or a criteria for which we do our data fit. Okay, so we are going to use something called the residual sum of squares. That is going to be, by definition, the thing that we want to make small when we do our data fit. And the way we define the residual sum of squares is it's just the sum over all our data points, I going from 1 to n, of our prediction error, epsilon I, squared. It has other names. Sometimes people call it the sum of squared errors or the sum of squared residuals. And there's a nice Wikipedia page if you click that green link. Have a nice long page about it. But we can also write this a slightly different way based on the equation on the previous page. We can write this in terms of yi and yi hat like this. In either case, the important thing to realize is that both epsilon I and yi hat, these are functions of our betas, right? So as I change the betas, as I change the model, we're changing the errors, changing the predictions. And so that is how we can finally design our model. That's how we can choose our betas. We can choose them so that this RSS is as small as possible. And this is probably something that you have seen many, many times in your life. It's just called least squares fitting. So least squares fit is just a very, very simple example. It's the simplest possible example maybe of machine learning where you have a data set, you have a squared error as your criteria, you have some parameters to adjust, and you just optimize those parameters to minimize the squared error. Here, turns out that your predictions and your errors are linear functions, your parameters, so all the math works out really nicely, and you can do this just with a simple derivation that we'll do in a few slides. So coming back to the visualization, you could say that what we're doing at the end of the day is we're tilting and moving this red line around so that the sum of the squares of those green lines are minimized. Sum of the squares. Okay, so that's what we're doing. Is everybody, yes?
Why do we not use just the absolute value?
Great question. We could use the absolute value, and in fact, in some cases, we would get better performance if we did. The reason we're not doing it right now is that there is no nice derivation that I can do on paper which will tell me the values of the betas that solve that problem. It's a more complicated problem. It's a convex optimization problem. If you've taken a course on convex optimization, you may even recognize it and say, yeah, I know how to apply an algorithm to solve this problem. But it's not something that we can do with a derivation. It's something you actually have to run a numerical algorithm to solve. So that's why we're not doing it right now. We're focusing on this easier case. But there are advantages to that. In fact, when you have outliers in your data set, when you have a few points in your data set that are way off, then that absolute value loss will actually be much more robust than a squared loss. And you would actually, if you knew about that and you knew how to optimize it, you would be better off using that absolute value loss. But yeah, we're going to talk about that a little bit later in the course, but for now, we're going to focus on this easier case.
So for a simple regression, is this where the learning happens, the memorization?
Yeah, you could say that we are learning those parameters beta 1 and beta 0 from our data to minimize this particular loss. Other questions? No. Okay, great. Everybody with me so far? Okay, so what we've kind of uncovered is really a very general recipe that we're using here, but actually it applies much, much more widely in machine learning. So it goes like this. We start by assuming a model with some parameters. In this case, we're assuming that our data follows a linear model, and our parameters would be beta 0, beta 1. Then, in order to actually learn the model, or learn the parameters, we have to get a bunch of training data. In this case, those are pairs of xi, yi's. Then we have to choose a loss function. In this case, we're going to choose this residual sum of squares. And finally, we have to find the parameters, in this case, beta 0, beta 1, that minimize that loss. So this is just an optimization problem, and we're going to see this a lot over the term, so you'll get good at recognizing these problems and solving them. We're going to talk a lot about that. But there's actually whole courses on optimization that teach you much more generic ways to think about these sorts of problems here. Okay. So this is basically, we're seeing it here, but we're going to see this over and over again as we go through the course. What's going to change are the models, the losses, obviously the data sets, and even the kinds of ways we have to approach optimization, because right now we can do it on paper, but later on we won't be able to do that. We're going to have to be much more sophisticated about how we do the optimization. Okay, so far we haven't used anything about statistics, but we're going to start talking about statistics now. And does anybody know the definition? What is the definition of a statistic? Okay, a statistic is just a summary of the data. That's all it is. So it turns out that for this problem, your data set could have like millions of samples, potentially. But if you know what you're doing, you can boil things down to 5 numbers. You can boil all that data down to 5 numbers, and with those 5 numbers, you can solve this problem optimally. And those 5 numbers are just particular statistics: mean, variance, and covariance. That's it. So let's just talk a little bit about these summaries of the data. And they, in some sense, tell us a lot about what matters for this problem and more generally for machine learning. So the first quantity, and I think you've all seen these before, but it doesn't help to go through them again. First quantity is the sample mean. All that means is you take all your xi's, you sum them up, and divide by the number of them, n. Just looking at the sample average. So that's what you have for your features. So xi, those are the things you're using to predict. This is just the average value. We're going to put a bar on it and call this x bar. We can do the same thing with the targets. We just average all of our targets, yi, and we get a y bar. So when you look at this plot here on the right, let's say our data was the red. So here I'm showing you a histogram. So we're looking at the different values the data takes on and how many times we see that value. And from here you could say, well, mostly my values are centered, my data is centered around this value. That's the mean. If I had this blue data set, it turns out that the mean, I believe, was constructed to be the same. Okay. So that just tells you basically what the data is on average. You also might care, well, how much does the data vary from its average? That's what the variance tells you. So this is the sample variance, which is just something you can compute directly from the data itself. So you take the sample xi, you subtract its mean. So now you have the difference from the mean, and now you just look at the average squared value of that difference. So you square it, you sum, and you divide by the number of samples. And of course, we can do the same thing with our target variables, yi minus y bar, square them, add them up, and divide by the number. Okay, so those are the variance. And so the variance tells you, again, the spread around the mean. One thing that's a little bit inconvenient about the variance is it's a squared quantity. So when you look at a plot like this and you say, how much does the red data deviate from its mean, you're sort of talking about maybe like, okay, it deviates about that much, plus or minus. But here you're not actually talking about the variance, you're talking about the square root of the variance, because you're looking at the data here, so you're looking, does the data vary this much or that much? You're not looking at the squared data, looking at the data itself. So these are squared quantities. If you just look at the square root of the sample variances, you get the sample standard deviation, and those are the things that are easily visible from that histogram. Okay. So one comment is some of you may be looking at these formulas and you may be saying, well, I've seen that formula before, but sometimes I see it with, instead of an n there, I see it with an n minus 1. How many of you guys have seen that? Okay, so that is another way to compute, or let's say to estimate the variance, the true variance in the underlying data set. It's what's called the unbiased estimate. We're going to talk about this in Unit 3 in a lot of detail. But for right now, I just want to say we don't actually want the n minus 1 there. We really want the n there, because the n there will make all of our derivations a lot easier. There are reasons to use it or not use it, but here we're not using it. Another comment I'd like to make at this point is some of you guys, I think all of you hopefully, you've learned about random variables at some point in your lives, random quantities, right? And you've learned about the statistical mean and the statistical variance, things like expectation. That is different than this. They're related, but they're different. There is no expectation going on here. There are no random variables on this page. There are just sets of numbers and averaging numbers in that set. So I don't want you guys to get the sample mean here confused with the statistical mean, or sometimes people call it the population mean. Okay. So like, for example, let me just give you an example with a coin flip. Maybe I have a coin and I flip it n times. And maybe I have a perfectly fair coin so that every time I flip it, on average, I should get 50% heads, 50% tails. So if I flip it n times, then the mean of the number of heads I get should be n over 2. That's the true population or statistical mean. But when I flip it n times, I may not necessarily get n over 2 heads. I might get no heads or 1 head or all heads. That you would measure with this sample mean. You actually plug in the actual values you got, the actual coin flips, and you just average them. That's the sample mean. So it's related, but it's different than the actual true statistical mean. Does that make sense? Okay, we're going to get into the statistical mean later, but for now, we're just working with these sample quantities. Sample mean, sample variance. Okay, so, and again, the reason why we're doing this is I'm going to try to convince you that if you know these quantities, all you have to do is boil your data down to these quantities, and then you can do our learning from them alone. You don't have to work with the data. Okay, so just for a little bit of practice here, what do you think the sample mean would be of the horsepower based on this picture? Guess.
Like 100.
About 100. Okay, sure. What about the miles per gallon? 25, right. So yeah, so I think hopefully you're just kind of visually saying like where can I slice this so that half is here and half is here. You can kind of visualize it maybe like if you put this on, if you had this shape and you balanced it on something, where would it balance? That's another way of thinking about where the mean is, somewhere around here. Okay, and then what about the standard deviation? So in that case, we want to, take our mean, maybe it's here, and then we want to say how far on average are things away from that. So what would you guess for the horsepower the standard deviation would be?
20,
30, 20. Okay, sure. We'll check. We'll actually compute them in a couple slides, but yeah, it's just kind of an exercise. to estimate them just so we understand what's happening. And just for reference, if we had a Gaussian distribution, one of these kind of bell-shaped distributions, then it turns out that 68% of the points are within 1 standard deviation, 95% within 2, 99.7 within 3 standard deviations. So it kind of gives you an idea of how much of the mass is collected there within that many standard deviations. Okay. So, of course, we don't have to guess. We can do this pretty easily with the NumPy package in Python. So we've already configured x and y. These are NumPy vectors. So we can use the NumPy mean command. So that would be, you would just call np.mean, and then that would return a value. And then we can print out these values, and we'll find here that it's 104.47 was the mean here. 23.45 was the mean here. And then our standard deviation for x was 38.44. For y was 7.8. So that's what NumPy gives us. Now, we need one more thing. So we've talked about the means of our targets and features, the variances of our targets and features. We need one more important quantity, which is the covariance, which tells us how the targets and features are connected. So this quantity looks a lot like variance, except it involves both x and y. So what we have to do is, similar to variance, we have to subtract the sample mean. So you take xi, you remove its mean. But then you take yi and you remove its mean. You multiply those quantities together, and you average that over your data set. Okay, so so it gives a rough indication of how related x and y are, and it's related as a very ambiguous term. There's many different ways in which you could measure relationship between them, and this is just one of the ways, one of the simplest ways. So basically, as x and y are more and more related to each other, that covariance will grow larger. If x and y are completely unrelated to each other, we would expect to get a variance or a covariance of 0, roughly speaking. We can be a little bit more precise. So one of the other kind of issues with the sample covariance that's not so convenient is that if you have the same data set x and y, and all you do is you double the values of both, you make double x, double y, what's going to happen to the covariance? So I've doubled x, I've doubled y. It's not getting smaller. 4 times, right? Because I will get a gain of 2 here, and I get a gain of 2 here. 2 times 2 is 4. So even though I really haven't changed how much x and y are related to each other, I've just scaled them, and all of a sudden the sample covariance is 4 times. There's something weird about that, something not so convenient. So it turns out the sample covariance is not related only to, it's not just about how related x and y are, it's also about how powerful or how large those values are. So sometimes, rather than looking at the sample covariance, we actually want to look at something a little bit more interpretable called the correlation coefficient, where what you do is you take your sample covariance, SXY, and then you divide by the sample standard deviation of x and the sample standard deviation of y. And this corrects for that scaling issue that was kind of bothersome. So now if you look at this new quantity, rho xy, if you scale your data set, like if you scale your x's and y's, rho xy does not change. In fact, if you scale just the x's alone and not the y's, rho xy won't change. Because what happens is, I mean, you can kind of see it. Let's say I scaled the x's alone. So I scale this by 2, this will grow by 2, but then this will also grow by 2, and they'll cancel. So that makes it really convenient. So now when you look at this correlation coefficient, it's really just about how much is x related to y. And actually, this guy lives always between -1 and 1. Can never get bigger than 1 or smaller than -1. So when you see a correlation coefficient of 1, you basically know that x and y are the same up to a scaling. Or when you have a correlation coefficient of -1, they're again they're the same up to a scaling, but that scaling is negative. So here are a couple examples where we can visualize, x on one axis, y on the other. What kind of data sets would give us 1? So this is a little misleading. To get exactly 1, all the points would have to fit exactly on a line. They're completely related. And actually that line could even be tilted, but all the data has to go on a line. Now, as they start to fall off that line a little bit, the value comes down from 1. And as they get more and more off the line, but still you can kind of see that there's this overall positive relationship. As one gets larger, the other still gets larger. You still have a positive correlation coefficient. Then you get to this point where there's absolutely no relationship between them. If I make one bigger, that doesn't tell me anything about the size of the other. That would be no correlation. You'd say they're uncorrelated. And now, go the other way, they actually kind of have a negative trend. And at this extreme, they're on a line with a negative slope. Okay, so that's kind of the range of how you can get different correlations. There's a nice Wikipedia page. This is not the only way you'll see data. I have another picture coming up. Let's see. It's coming up later. We'll look at it later. But does this kind of give you an intuition about this correlation coefficient? Okay. Yeah, it's a nice scale-free way to understand the correlation or the particular relationship between x and y. Okay, so basically with these 5 statistics, that's going to be enough for us to perfectly design our betas. In other words, the betas that will give us the smallest possible RSS. But before we do the derivation and go through all those details, I want to point out that there's a couple other really useful expressions that pop up a lot, and it's good to know about them and see them and be able to recognize them. So the first way that we define the sample variance was like this. So you take xi, you subtract its mean, square it, and then average all those over I. But there's a very useful alternative formula where we can write things in terms of the mean squared and the... Okay, we'll just see how this works. So let's say you take this guy and you expand this square. So we write this as xi squared, and then we're going to have the cross term. We're going to have 2xi x bar, and then finally a negative 2xi x bar, and finally we're going to have x bar squared. So that's what I've done. So I have 3 terms in here. They each get averaged, but I can also write that as the average of those individual terms. Is that clear how I got from here to here? Okay. So this last one, when I took the average of this squared, if I have a quantity that's just repeated over and over, and if I average it, it's just like that quantity once, right? So that's why this sum or the average disappeared there. Okay. Okay, so we have this expression. So what we can do is we can notice that, what is this term here? Just the 1 over n. What's another name for that? X bar, right? It's the sample mean. So actually, now you can see that those last 2 terms combine. We have minus 2 x bar squared and plus x bar squared. So we just in total get minus x bar squared. So finally, we can write this as 1 over n like this. Okay, so the upshot of this is that when you see this expression, which pops up a lot, it's the average of the squared value of xi, that's what this is, that equals this plus this, right? I can just move this to the other side. So that equals the variance of x plus the squared mean. So this is a super useful thing to know because it pops up all the time. So we can do something very similar. The steps are pretty much identical with this sample covariance. We can expand this into 4 terms, do a little bit of simplification, and what we find is we get 1 over n sum over I of xi times yi, that thing minus x bar, y bar. And that implies, after just moving things around a little bit, we have 1 over n times the sum of xi, yi. That thing is just this sample covariance plus the product of the mean of x and the mean of y. So this is another super useful relationship that shows up, and we will be using these in our derivation because they'll show up there. Make it really convenient. Okay. Have you guys seen these before? I'm pretty sure you've all seen them sometime before in a statistics course. But maybe you've forgotten them, and that's fine. But they're very important, so you have them here. So here's a little, are there any questions, by the way? Yeah.
I have a question about notation.
Sure.
So you have x bar times y bar.
Yep.
Which is just the means multiplied together.
Right.
Here in the notes, it just have like x, y, 1 bar of the whole thing. I just want to make sure that that's not different.
So I think what happened is it just got formatted where there was no space between them.
Okay, so if I see that again, can I just assume that it's x bar, y bar? Or
Yeah, that's just like a weird formatting thing. So that's just how LaTeX formatted it. But yes, it was meant to be x bar, little space y bar. Sorry about that. Okay, so here's just sort of a summary then of these 5 statistics that we saw, what their names are, what their notation is. So we have, the sample mean of x. We have the sample variance of x. There's actually 2 ways we can write this. We can write it as sx squared. That's how we defined it. But if you think about it, if you write sxx, where remember, like, this is like similar to this, right? Imagine that for this y, I plug in x. That would mean that I have xi here and x bar here. At that point, I have exactly this thing over here. So the sample variance is really like the sample covariance between x and itself. So you can write it 2 ways. You can write it like this, sx squared, or write it sxx in a subscript. 2 common ways to write it. And the sample standard deviation, this is nothing more than taking the square off here, or if you want to think about it, taking the square root of that sxx. In terms of the formulas, so this was our formula for our sample mean, formula for our sample variance. This sample standard deviation is just that square root. Sample covariance, we saw this. And finally, we have our sample correlation coefficient, which is just this covariance normalized by those sample standard deviations. In Python code, try to be consistent. We will try to be consistent in the demos and stuff, naming things xm for the mean of x, sxx, sx, sxy, rho xy. Okay, so I think it's a good point to stop for today. Any questions on anything? All right, have a great weekend. See you on Monday. Remember, Monday, 4 p.m., linear algebra, homework 0 is due.